So my thesis is entitled "The Analysis of the Thermal and Hydrological Performance of Green Infrastructures in Subtropical Climate." And I divided the thesis in 7 topics, but due to the limited time that we have here today, I'll be only presenting 3 papers. So the Appendix A and B, I will not be presenting, but feel free to make suggestions on those papers. And also, I would like to say that one of those papers, the Appendix B, I guess, it was a paper that we published from data monitor previously from my doctorate. So it was a period of the time that the experiment was going on, but another student was carrying the experiment. So the first topic is the introduction, and we know that the strategic use of green infrastructure, including trees, green roofs, and green walls, can help to control the microclimate of the building without needing to increase the energy-consuming strategies, and still offer many additional benefits, such as improving human health, stormwater retention, creation of habitats for other species, the noise attenuation, and the temperature reduction. So in order to investigate these potential benefits, we also need to consider the climate in which the system is located. And to do that, we need also to use weather files. So weather files can take different formats, like such as the test reference year, the typical meteorological year, and they are composed of data corresponding to 12 months of different climatic parameters, such as temperature, relative humidity, solar radiation, wind speed, precipitation, atmospheric pressure. And these values, the data monitored, is derived from long-term data sources. And many times these weather stations present inconsistencies and errors, which why it's important to continue to update the monitor data from these weather stations. And since green infrastructure's performance is influenced by the climatic conditions, we also need a comparative studies across a range of climate zones, especially for countries like Brazil that do not have standardized regulations for green roofs and green walls. And we base our design and the choice of materials and installations methods on the FLL guidelines from Germany. So with that said, the objective of this thesis is to analyze the thermal and hydrological performance of green infrastructures by monitoring and modeling climate data. And the specific objectives are 4, and each one of them generated a paper that composed the thesis, with exception the last one that was developed before my doctorate. So the first objective is to process and analyze the climate data of Santa Maria over 18 years to generate a more reliable weather file. The second objective is to develop a mathematical model of a vegetated wall by monitoring the internal and external climate variables of an affordable house with a green facade in subtropical climate of Brazil, and to characterize its heat flux balance. The third objective is to evaluate the similarities and the differences between green roof structures built in the CFA and the CFB climates. And the last objective is to investigate the influence of the drainage area on green roof hydrological performance in a temperate oceanic climate. So the first paper is already published and is entitled "The Correction of Precipitation Data in Weather Files for the Subtropical Climate in Southern Brazil." So this paper is published in the Sociedade de Natureza journal. It was published earlier this year. And before this paper, we had a few weather files available for the city of Santa Maria. And the most recent one was built in 2014. And presented inconsistencies regarding the precipitation data. So because of that inconsistency, we wanted to generate a more reliable weather file and to correct the errors in precipitation. So Santa Maria is a subtropical city with average annual temperature around 19 degrees during the summers, and it's common that the maximum air temperature reaches up to 40 degrees and during winters usually drops down to negative values. So the rainfall in the city can be considered evenly distributed throughout the year, and the annual rainfall is around 1,600 millimeters. So the method adopted to generate the new files started at the data gathering from the INMET database, and the data included hourly values from 2002 to 2020 of dry bulb temperature, dew point temperature, wind speed, atmospheric pressure, wind direction, and of course, precipitation. So since there were gaps in this data that we collected from INMET, we also applied a filling procedure. And this filling procedure, it varied according to the number of consecutive failures. So in gaps that we had 6 missing values, we just did a simple interpolation. For gaps with more than 6 values but less than 24 values, we chose the closest 10 hours, the 5 hours before and the 5 hours after the gap, for the 3 days before and the 3 days after the gap. And then we did an average difference of the data in addition to the standard deviation and the variance. So the day between these 3 days after and the 3 days before, with the smallest difference from the day with the gap, was the day used to fill the gap. And to verify any sign of significant inaccuracy of the data and to perform some data quality, we also applied range tests to evaluate the maximum and the minimum limits of each climatic parameter, and steps tests to evaluate the maximum difference between 2 consecutive data. And the last one is the persistence test to evaluate the standard deviation and the variation in the 24-hour period. So to find the test reference year, which is the TRY file, we did a calculation of monthly average dry bulb temperatures of the entire weather data, and we eliminated the years with data that contain extreme monthly average temperatures, even if it's high or low, until only 1 year remained. And that year, in this case of this study, was the 2017. And for the typical meteorological year, we performed the same analysis for each month independently. So the selected months can be from different years, and we had an unreal year set. So after the TRY and the TM2 were generated, we used the spreadsheets from the Federal University of Viçosa to calculate the solar radiation data. And then we compared the 2 files. We compiled the 2 files into comma-separated value format to generate an EPW file. And to compare these 2 files with the previous files that we already had for the city, we did a building simulation considering the K600 from ASHRAE. So for the results, I want to highlight the temperature and the precipitation comparison, because those 2 values are the most significant in the weather file. So the temperature, when we compare to the other files, we can see that the values are pretty similar in all the weather files, with average temperatures ranging from 18.4 to 19.8 Celsius degrees. And this result can indicate that the 2 weather files that we developed in the study are consonant with the previous files that the city already had. And there were no errors in temperature. But when we consider the rainfall data, we can see from the figure 2F that some weather files, previous weather files, contained null data for the 2nd and 3rd weather files, and lower data of precipitation for the 4th weather file, which clearly indicates that these files had errors and did not consider the rainfall data. And when we see the annual cumulated precipitation, we can see, for example, for the TMY 7317 was around 200 millimeters. And even though the TRY 03, which was the test reference year before we updated, it was around almost 900 degrees. It did not reach the annual accumulation data. And when we see the 2 files that we developed for this study, which are the TMY 0220, is around 1,700 millimeters, and the TRY is around 2,117 millimeters. So those values of precipitation are in accordance with the climate normals for Santa Maria. So when we compare the previous files, weather files, with the two developed in this work, we can see the average daily temperatures are very similar between them, although the typical meteorological year changed from 2000. The typical meteorological year and the test reference year differed. So regarding the TRY file, which are the test reference year, we saw that from 2003 it changed to 2017. And however, this file resulted in higher average operative temperatures as well as higher global solar radiation. This can be justified because of the climate change in the recent years. And we also see that this significant variance can impact on the energy consumption, and also the other weather parameters can do that as well. So for the second paper is entitled Improving Indoor Environmental Quality in an Affordable House by Using a Vegetative Wall. So in this paper, it has not been published yet, but it is intended to be submitted to the Building and Environment Journal. So in this paper, we analyzed the heat flux balance through two walls, a vegetative wall and a bare wall, and we compared the two walls to see how the plant coverage could reduce the heat fluxes through the walls. So we monitored various climate parameters, such as the external and internal temperatures, the wind speed, the solar radiation, the surfaces temperatures of the walls, every 5 minutes over 2 years. So with that database, we adapted a mathematical model based on Susarova's method to calculate the conductive heat flux, the shortwave and long-wave heat fluxes, the convective radiation, and the evapotranspiration. So since this is a deciduous plant, we wanted to see the heat flux differences throughout the season. So we set up 3 scenarios for summer and 3 scenarios for winter. So here you can see some equations based on the Susarova's method, and these equations take into account many parameters, such as the wall and sky and ground emissivity, the temperature of the ground, the temperature of the surfaces, and each one of those parameters was whether assumed or monitored in the camp. So for the scenarios, we set up 3 scenarios for winter and 3 scenarios for summer based on the leaf area index and the transmissivity value of the plant. So for the summer, we chose to fix the transmissivity value since the plant is really dense in the summer and did not lose its leaves. And in the winter, it changed. So we changed according to the leaf area index of each one of these pictures. So for the results, we can see that in the cold winter day, both walls lost energy during the night, and the bare wall gained energy during the day. And the highest variation between the heat fluxes showed that during the day, the conductive heat flux on the bare wall was around 83% higher than on the vegetative wall. And this shows that the plant can positively act as an insulation barrier, preventing the surface behind the plant to excessively heat. When we consider the cumulative long-wave radiation fluxes, we can see that they were almost always negative for both walls. And the results show that the long-wave radiation is always higher for the bare wall than it is for the vegetative wall, except for the hot winter day. And during the daytime, the vegetative wall lost on average 38% less long-wave radiation than the bare wall, and during the nighttime around 50%. The maximum difference between the two walls was recorded on a cold summer day, and the vegetative wall lost less long-wave radiation energy than the bare wall due to the thermal barrier effect provided by the plant layer, even during the winter when it lost its leaves. So since the wind speed, we only monitor it for both walls and not individually for each one of the walls, the convective heat fluxes were calculated for the wall as a system. They were not calculated for each one of the wall. So the maximum convective heat exchange, which is 5 watts per square meter, occurred on a hot summer day, and the convective heat flux heat fluxes were generally positive during the day and negative during the night, when the wall lost convective energy. And this is primarily due to the surface temperature of the walls and the wind speed near the walls. So when we see the analysis of the solar radiation for the 6 scenarios, it was concluded that the bare wall received more solar radiation than the vegetated wall. And in all scenarios, the average solar radiation absorbed by the bare wall was 48% greater than the vegetated wall. So for the latent heat, it depends mostly on the net radiation. And the net radiation depends mostly on the shortwave radiation. So the shortwave radiation heat fluxes takes into account the total solar radiation incident on the surface and the transmissivity, that it depends on the typical day that we are considering, in the absorption factor of the wall. So since this transmissivity varies between winter and summer scenarios, the latent heat changes in function of these factors. So for example, solar radiation varied slightly between typical summer days, but with high values of around 6,000 watts per square meter between the 3 summer days, and the transmissivity was generally constant, a value of 0.25. So this was were the results from the second paper, and the third paper is entitled "The Retention Performance of Green Roofs in Subtropical and Temperate Climates." So in this paper, we compared 6 green roofs, 3 of them in Brazil and 3 of them in Germany, by monitoring their runoff and retention performance over several years. So the 3 green roofs installed at the Federal University of Santa Maria are named BR1, BR2, and BR3. BR1 had an area of 6 square meters and was composed of prefabricated box-shaped modules made of recycled EVA and agglomerated with CP5 Portland cement, with some ash addition. So the vegetation comprised a mix of popular and typical regional species, and the BR2 green roof, which are represented here in the figure 2B, had an area of 6.75 square meters and was constructed with a commercial system comprising interconnected hexagonal modules made from recycled PET, and the vegetation used in this roof was sedum. The BR3 was the larger green roof with an area of 12 square meters and comprised a layer of commercial geocomposite double membrane of 10 millimeters, over which a layer of gardening soil of 80 millimeters and sedum were added. And the monitor system used for these 3 green roofs was standardized and consisted of a tipping bucket rain gauge with a 0.2 millimeter precision and a recording time step of 5 seconds. And the hourly precipitation data that were monitoring the green roofs was compared and verified against the weather station that are situated near to the experimental area. Regarding the German green roofs, they were located in 2 different buildings in the Neubrandenburg University of Applied Sciences. So in the building 3, we had the DE1 and DE2 were built, and they were made from Ullapore and Optima commercial growing medium. The DE1 in the figure 3A had an area of 150 square meters with a substrate layer of approximately 10 centimeters of crushed expanded slate, and the underlying structure was integrated into the green roof surroundings, while the DE2 had an area of 206 square meters and a substrate layer of 10 centimeters composed of crushed expanded clay, expanded slate, lava, and pumice. And the DE3, which is the green roof represented in the figure 3C, was built in building 2, and it had a zinco commercial growing media plus a drainage area. And the vegetation used was grass seeds and sedum cuttings. The monitor used in the German green roofs were similar to the one that we use in the Brazilian green roofs, which consisted of a tipping bucket rain gauge with 0.2 millimeter precision and a recording time step of 5 minutes for retention data and was placed in each one of the green roofs. So this bucket had a volume of 1 liter, and when the bucket was full, it tilted a triggered a sensor that counted upwards. And they also had a manual ombrometer rain gauge with a 0.1 millimeter accuracy, and was positioned in each green roof to monitor the precipitation at the same time step as the tipping buckets. Additionally, as we did with the Brazilian green roofs, we have verified the data, the hourly precipitation data, using the Trollenhagen weather station, which is located near the experimental area. So the data were collected at each of the experimental site and analyzed event by event. So a rain event was defined as a period of precipitation followed by 6 consecutive hours of no precipitation. And the precipitation and the runoff values of each green roof were used to calculate the retained volume and the long-term runoff coefficient for the data using equations 1 and 2. So similar to previous studies, the evaluation of the green roof retention performance was based on the rain event, the size of the rain event, so small, medium, and large events. However, when we are comparing two locations with such a significant discrepancy, the annual precipitation between the two locations are very different. So instead of fixed values in millimeters, we changed the classification to the percentage of monthly average precipitation. So for each of the two sites, we chose small events to be less than 15% of the monthly average rainfall, medium events between 15 and 30%, and larger events higher than 30% of the monthly average precipitation. So since not all the rain events were considered, because we had some equipment malfunctioning or gaps, there is a difference between the rainfall monitored at the green roof and the precipitation at the weather stations, as you can see in the graphics. So the cumulative stormwater retention performance based on the average data was 48% for BR1, 43% for BR2, and the higher retention occurred on BR3, which are 72%. And this difference in the values can be justified by the different constructive characteristics of each green roof and the scale effect, since we had a constant retraction and expansion of the substrate along the perimeter. And we also had the shrink swell substrate with high content of clay, and they can affect the retention performance. Also, we had different periods of monitoring for each green roof, and then this can influence the results as well. So regarding the green roofs in Germany, we can see that DE1 presented a retention of almost 75%, DE2 higher than 75%, and the DE3 had the lower retention rate equals to 50%. So when we compare the two climates, we can see that the total precipitation in Santa Maria is higher than in Neubrandenburg, and this can indicate that the reduced rainfall amounts increase the total retention percentage and show a connection to the climate. And another important factor that we must consider between the two climates is the green roof area. So the green roofs in Germany are consistently larger than the green roofs in Brazil, and this can show a higher impact of the scale effect influence. So in the previous studies that we used to see that they evaluated green roof retention according to the rainfall event size. So Persch, for example, 2021, saw that the rainfalls were normalized and then clustered into 3 thresholds based on the monthly average rainfall. So for Brazilian green roofs, we saw the retention values range from 0.07% to 100%. And the total rainfall depth for all the events varied between 0.2 millimeters to 68 millimeters. And this can indicate that numerous events with a variety of different rainfall characteristics were included in the analysis. So overall, we had a decrease in the percentage of stormwater retained, as stormwater size increases. This for the Brazilian green roofs. So the average retention of small events for Brazilian green roofs was around 82%. For medium events was 56%, and 38% for the large events. So for the German green roofs, the retention values varied from 20 to 71%, and the rainfall depths range from 1.2 millimeters to 81 millimeters. And the German green roofs presented closer retention percentage for each event category, possibly due to the lower rain intensity in this climate. So when we compared the percentage retention of green roofs from each climate for each event size, we saw that BR3 presented the best performance for all events, and the DE2 had the best performance for both medium and large events. And those two green roofs are the green roofs with the larger area between the Brazilian and the German green roofs. So here, I just like to point out that the Appendix A had the paper entitled Scale Dynamics of Extensive Green Roofs in Temperate Oceanic Climate. And I will not be presenting this paper, but we are looking forward to hear your considerations and suggestions to improve this paper. In the Appendix B, we have the already published paper, which is a year assessment of the suitability of a green facade to improve thermal performance of an affordable house. So for the conclusions of the thesis, we had that the benefits of green infrastructures include the multidisciplinary field, as several studies identified the systems, the green infrastructure systems, as one of the sustainable solutions for both buildings and cities. And the performance of green roofs and green walls is influenced by many factors, especially the locations, as we can see in these papers. So comprehend how the climate affects the performance of green infrastructures are not fully explored, and we can explore it even more to fully employ these infrastructures in different regions where this practice proved to be less efficient because of the less knowledge that we had. So we saw from the first paper, for example, the importance of updating the weather files in time intervals shorter than 30 years. And we compared the two weather files that we developed in the first paper. We saw that the precipitation data was much more similar to the reality when we saw no errors and inconsistencies in the files. So regarding the second paper, we saw that the heat flux balance analysis showed that the vegetative wall acted as an insulation system, regulated the building's temperature, and prevented the overheating of the walls. And this can show a potential of a low-cost green facade to improve thermal comfort, even in a low affordable house. So we do not have to invest a lot of money to achieve a great thermal comfort. For the third paper, we saw that there was a link between the precipitation and the rotation data, indicating that climate factors such as temperature, relative humidity, and net radiation can impact the retention performance. And we also saw the climate conditions also impacted the heat flux balance through a vegetative wall, and highlight the importance of the constant update and monitoring of weather data. In addition, regarding the lower levels of precipitation, they can result in higher retention performance, and this can indicate that the range of event classification can modify the results. So depending on the classification of events that I choose to analyze my results, they can change the results. And I also brought here the findings of the fourth paper, even though I did not present the paper, to show that similar results were found for this paper in agreement with the third paper. So where green roofs with larger surface area outperformed smaller roofs in terms of rainfall retention. So for future research, we recommend that the elaboration of a database for plant parameters, such as leaf area index, leaf absorptance, leaf average dimension, and among others, could be monitored and measured to use more accurate values in the mathematical model. In addition, the same recommendation can be made for green roofs in subtropical climate. So the majority of studies about green roof infrastructure addresses the benefits and the performance of the extreme seasons, which are the summer and winter. However, here in Santa Maria, we can see that during spring and autumn, we have a lot of changes in the leaves of the plants. So in order to increase the thermal comfort and to see how the plants can be influenced by those two seasons, another future studies could perform parametric analysis evaluating the transition period between hot and cold seasons. So these are the references some of the references that I use for the thesis. And thank you, and I'm open to answer any questions or to hear any considerations or suggestions you may have. Thank you.